to connect, learn, and grow together. Our mission extends beyond just technology. It is about empowering each other to imagine, innovate, and make a meaningful impact. It is so wonderful to see the amazing turnout today, and I'm so happy to see that we have people joining us from all over the world. Now, a little about our chapter and what we're doing right now. We are excited to focus on our Road to Google Developer Certificate series, targeting the professional machine learning certification. This initiative is designed to elevate your skills in cloud technologies and machine learning. As part of this series, we have 7 sessions lined up for you, out of which today is our second session. And we have some thanks. We are thrilled to collaborate with GDG Seattle for these series. So a shout out to them, bringing together the best instructors and experts in the field. This partnership helps us ensure that you receive top-notch guidance and support as you prepare for the certification. GDG Seattle's team's expertise and support has been invaluable in making this certification series more meaningful. Now a shout out to our home team. A big shout out to GDG Surrey's steering team, whose dedication and hard work make these events possible. Watching this team work every day to make these series as beneficial as possible for our attendees gives me so much pride to be part of this versatile organization. Now, in case you missed the information session, which was on Feb 3rd by our Google developer expert Vasudhev, the session provides a detailed overview of what to expect in each of our sessions in the certification series. Now, if you couldn't attend the session, it is available on YouTube, and we just shared it in the chat as well as on our Discord channel. Now, moving on to our speaker. Today, we have a lightning talk. It is my pleasure to introduce our first speaker, Adam. Adam is the CTO and co-founder of 𝗕𝗲𝗃𝗃, a music streaming platform for artists to release their music incrementally. In his words, he likes to call it the GitHub for music. Adam has worked at a few video game studios in the past, most notably Electronic Arts on the FIFA team, and most recently as CTO of 𝗕𝗱𝗃𝗃 for several years. He is always looking for something new to learn and writes many of these learnings on his blog. It is devtales.xyz. I highly recommend that you check it out. It is so authentic. It is so from the heart, and it feels so real. Thank you, Adam, for joining us today. Over to you.
Awesome. Thank you for the introduction. I will give a warning. There's a lot of audio, and so I need to change sharing tabs to get the audio to come through. So just bear with that as it goes through. So yeah, really already introduced myself. My name's Adam, and I'll kind of maybe just start with kind of the motivation behind this talk. I have been exploring how to create voice changers, but specifically for singing. And so this is our platform here. I'm not going to go into the platform at all, but we use it to kind of showcase that there's different versions of things. And so what I'll first show you is an example of a model that I trained. I think this is the very first one that I trained. And basically what it starts with is an original version of the vocals. And then I'll show you a converted version afterwards. So we'll play this for a little bit here. No, I don't know myself anymore. It feels like the walls are all closing in and the devil's knocking at my door. Okay, so if you don't know who 𝗕𝗲𝗃𝗃𝗃 is or that song, it doesn't matter, but good music as well. So that one, using other AI, even kind of stripped out the backgrounds to get just the vocals. And then what I did is I crafted a model of John Mayer using some of his own vocals, and basically took that input audio from 𝗕𝗲𝗃𝗃𝗃 and had it converted into John Mayer's voice, essentially. So this is what that sounds like. You know,
Feels like the walls are all closing in the devil's knocking at my door.
So it depends on how much you know John Mayer as to whether you feel like that actually starts to sound like John Mayer. I don't think it's great, to be totally honest, but again, this is the very first thing that I did. And I found out along the way, I was using like a 10-month-old code. And then I've learned all kinds of things about cleaning up data sets and all that jazz. So that's really just the starting point. So that's kind of the motivation behind this. Today, I'll actually only talk about converting voices, but it uses the exact same tool. It's just the pitch is an additional layer. And the reason I use this tool, which we can jump over to here. Oh, right, I can do it that way. Nice. So this is the tool that I used for this, retrieval-based voice conversion web UI. It's actually been quite difficult to kind of find the actual information behind who runs this. But basically, as I understand it, I think it's a person from Japan. And so you can switch over to their English documentation, and they kind of explain it a little bit. The key stuff is kind of how to actually install it. And where we'll jump over to is here. So this is my Google Colab. I'm not sure how familiar people are with it, but I assume if you're here, you have some vague familiarity with Python and Jupyter notebooks. So it's kind of just a convenient way to run a Jupyter notebook. And importantly, get access to a GPU in the cloud. Right now, I'm just running on my MacBook, which obviously doesn't have a GPU. And this allows me to train things much more quickly and for way cheaper than it would be to buy that graphics card. So these I took from the actual instructions from this GitHub. So basically here we clone that repo, we cd into it, and then these are some system level dependencies that need to be installed, and then we install the requirements for it, and then finally we download the models. This takes a couple minutes, so I've already done it just so we don't have to sit around waiting. And you can kind of just see, yes, it went through, installed all the dependencies and all that. And then from here, you run their 𝗕𝗲𝗃 command. And I will run this now. And this will spin up the web UI that you can then use to access this tool. This takes a couple seconds, so we will wait for that. And great. And so then you click this link, and you'll see here I had to pass the -- Colab. That ensures that it creates this publicly accessible link instead of a local host, because you can't actually access Google Colab localhost. And so let's jump in here. This is the tool that was provided, and it's pretty neat and convenient how they present it. And so if you go to the train tab, this is where you do your training. And what I'll do is I'll create my live version of this. I've already pre-trained a model that we'll use to kind of compare to this. Here you can choose your target sample rate, 48 kilohertz versus 40. I think this slows it down a little bit, so we'll just leave it here. And then this is the interesting piece. For now, we'll turn this off, the pitch guidance, because we're just doing voice. But when I did my other model, you leave this as true. And then finally here it says enter the path of the training folder, which is going to be fun bouncing between tabs here. So back to my Colab, this is my training folder. And basically all I did is I dragged that file from my desktop here and then paste that path in here. And now it knows where to gather its training data. And my training data is essentially me just reading a book. For I think I recorded maybe 13 minutes of me reading a book. And then down here you get to choose some of your parameters for the actual training. From some of my own testing, I found the batch size of around 28 seems to kind of be okay for the amount of memory the GPU has. And because what I'm showing right now for the training, I just want to demonstrate how it works, and I don't want it to take forever. I'm going to turn this down to just 10, and then we'll save every 5 epochs. And then what you can do is click target this to yes, and then it'll make sure that when it saves every however many you choose here, it'll generate an entire full model so you can actually compare between the models. And once you've got that, you can just hit this one-click training, and it will do it for you. And so if we bounce back here, instead, we should be able to see the actual logs of what it's doing, and hopefully doesn't take too long. Does a few things. I think it ends up taking, so this is a single file, and I think here you'll see that it kind of splits it out into what I assume are smaller snippets of it so that it can pass it through its training. And then a few other things that I have no idea. And I'll take this opportunity to state for the record that I'm not a machine learning expert. I take tools that are available and I use them. So keep that in mind. And pretty soon we should get into the actual training. And unfortunately, it uses so much of the GPU that I can't even show anything else until it is done. But it's quick once it gets going. Okay, well, while that's happening, I'll jump back to it and we can see the logs. I can show the training data that I gave it. So again, here, this is a project where I'm experimenting with me in converting my voice. And so here you can hear
how Amazon took over books.
This is me just
Amazon dominates all of online retail, which makes it easy to forget
and
that
you can
it
see it's
started
13
with
minutes
books.
long.
When Amazon
there's
launched in 1994,
zero background noise.
it was the kind
That's
of
one of
business
the most
Warren
important
Buffett
things, because training this model is going to take everything that it sees or hears or however you want to call that, and might find its way into the model that ends up getting trained. Okay, we can jump back here for a second. So now we can see it's started to get into it, and it tells you what epoch it's on. It gives you how long that epoch's taking. Of course, for whatever reason, this is taking twice as long as I had done this morning, so that's fun. But I only did 10 epochs, so it shouldn't be too bad. And here you can see that it's saving out the entire model at the 5th model, and then it'll get back and get a few quicker ones, and then we'll have our final one. And so while, again, we wait for that, let's jump back here, and we'll take a look at the sample audio that I'm going to use to convert. And so if you don't know 𝗥𝗲𝗃𝗏, he's a podcaster that is a professor at MIT, talks all about AI stuff. So I thought that was a fitting clip to convert. And so this is how the original sounds.
Please allow me to say a few words about the possibilities and the dangers of AI in this current moment in the history of human civilization. I believe it is a critical moment. We stand on the precipice of fundamental societal transformation, where soon, nobody knows when, but many, including me, believe it's within our lifetime, the collective intelligence of the human species begins to pale in comparison by many orders of magnitude to the general superintelligence in the AI systems we build and deploy.
Okay, so that's how the original sounded, and I'm still delaying a little bit while these epochs finish up. So I'll showcase now a demo that this one was trained on my own GPU. So I have a desktop at home, and I was curious kind of to compare timings and all that jazz. So this was trained. I actually think the one that I'll show you that I did on Colab, I think is better than this. But this is what this one sounded like.
Please allow me to say a few words about the possibilities and the dangers of AI in this current moment in the history of human civilization. I believe it is a critical moment.
So you can kind of hear that it sounds a little bit robotic, and that's a thing that's fairly common if you kind of read through some of the issues with this model. A lot of that comes down to just kind of like training time, your sample data, and all that jazz. And so let's jump back here, and it should be writing out that last one. And once that's done, we can go back to the UI tool. And I think we should see at the very end of this guy here, when it's actually done, it should spit out a success. There we go. All processes have been completed. So if you weren't looking back at the logs, that's how you know you're done. And then you can jump over to this model inference tab. And so in here, you'll see a bunch of these here below. These are the ones I trained earlier, but this Atom Live is the one that we just trained. And so I'll first showcase this. This E5 means this is the one that's saved at that epoch 5. And I will grab the clip that I showed you that we're going to convert and put that in here. This is the file to process. Those are the only things you need to change, and then you can hit convert. And now we'll play that.
Please allow me to say a few words about the possibilities and the dangers of AI.
So you can hear there is, again, like they've got that weird robotic. You can maybe kind of start hearing my voice in it even, but also the quality doesn't sound super great. And just for time, let's maybe even just jump straight to the final model that I got. So this is after 200 epochs, maybe just under 20 minutes of training. And then you'll see here that there's some parameters, and I won't touch them yet. So we'll generate a first one without changing them. And listen.
Please allow me to say a few words about the possibilities and the dangers of AI.
So this one's interesting. The quality actually sounds pretty good, but when I first listened to it, I didn't actually felt like it sounded like me, mostly because his pitch is down too low. And so you can see here, it's got the transpose, which will actually change the pitch of things. And then another thing that I found helped here is this controls how much accent it's attempting to pull from your model. And it says too high as artifacting, and we'll see how this goes this time, but I cranked this all the way up and I actually found it was quite a bit better. So I'll have a listen to that.
Please allow me to say a few words about the possibilities and the dangers of AI in this current moment in the history of human civilization. I believe it.
So it's kind of weird when it's your own voice, because I actually don't think I know how to hear my own voice as well as other people do. But I think that sounds pretty good. And I think time-wise, that's pretty much about all I have time for. I would love to open that up to some questions, I suppose.
Oh my gosh, that was amazing. Guys, please feel free to leave your questions in the chat and we can pick them up. Yeah, I guess people are just going nuts. Do we have any questions, guys?
Yeah, I think people are just blown away.
Yeah. Because
Okay,
how can you
cool.
ask questions? Oh, okay.
What do you think?
What do you think are the ethics?
Yeah, I think that is the important question, but it's interesting because I don't think, like, legally it's gonna take way too long for legal to get caught up to this. And so I think we're stuck in a territory of just like having to trust that people won't use this for necessarily bad things, which in a lot of ways is kind of how our world works anyways. And so I think it's just up to people being good people, because I think we're like years away from actual laws where you can actually do anything about this.
Exactly. There's just so much that goes into making a regulation. You need like a blanket regulation, and we ourselves don't know what the capabilities are of these things. So unless we at least know like 50% of what these things can do. Yeah.
Watermarking, maybe, yeah. It's interesting though, with the ability to kind of, just podcasts alone, like people are already putting out very high quality versions of just them speaking. And that's pretty much all you need for training data. And it's really interesting. And so it's also kind of interesting because it's like, if you've recreated something, it's not actually their voice. And so where does that fall? And that's where I think like legally it falls into very weird territory. And I would say even ChatGPT has the same problem, where I would argue that ChatGPT is far more copyright illegal than this. of just full on taking people's actual information. The same goes for 𝗦𝗲𝗃 in the image creation. Like I think they have full on just stolen artwork and created a tool that they are now selling. That's a little bit more negative trending, but that was the question.
That's kind of what we see, right? When we have an emerging technology, they are dying for data. So people just jump over the ethics before, you know.
Neil's question here, what use case do you see for such a tool? I actually found it interesting, and it's part of what I was exploring on two different levels, but the same way. I actually, and you can probably even hear it now, I stutter a lot when I speak, but I also like to generate videos. And if you're trying to create a concise video, if you could just type in, hey, here's what I want to say, and have it say it in your voice. Like I want to have control over my own voice model. And so that's one example. And then a similar one, more on the music side of things, and this is my co-founder is the one who's kind of inspired this, is he'll actually hum a melody and then want to kind of experiment with different lyrics. And so to have his own voice trained, so it's all his own stuff, it's his own music, it's his own voice, but to be able to go, what does this sound like with these lyrics? What does it sound like with these lyrics? Without having to do a perfect recording every single time. And then also just to catch that last question there on, can it be done in different languages? Yes.
I guess we come to the end of Adam's session. Thank you so much for this wonderful session, Adam. Like, it is so rare to see projects that actually are not some just a classification model. It's so cool to see that you're putting these products out there. Just a shout out to Adam's startup, 𝗦𝗃𝗃𝗃𝗃 and his blog, and Adam will share his links if you'd like. Sure. And all that. I'll just share my screen again. Hi, Via.
Before we proceed with the next bit, I think Ankit is saying that I just attended the first class of ML in my life. I feel very interesting, but I am not able to understand so much. Yeah, I think that's, once you start digging a little, once you take the sessions like these, or there are courses on Google, and we provide you credits for that when you RSVP with us. So you can go to Google courses and take the beginner level courses, and it would be really, you'll understand more. That's the whole part of this learning journey and study. And if you need any support, our mentors are here. Please reach out to us on Discord. We will try to break down the concepts as much as we can. And our team is open to helping you. So you have to just reach out to us.
Yeah. Just reach out to us. We're happy to help.
Yeah.
We're very passionate about this. So we'll move forward then? Yeah. Okay. It is my honor to introduce the instructor for today, 𝗦𝗃𝗃𝗃𝗃𝗃. Vasudev is a Google developer expert in Google Cloud and a seasoned professional serving as a staff data engineer at the Admiral Group. With a wealth of experience in the realms of Google Cloud Platform, big data, and data architecture, Vasudev has consistently demonstrated his prowess in implementing industry-led products recognized by Gartner. Thank you for joining us again, Vasudev. It's great to have you back. Over to you.
Yep, thank you. Thank you for having me again. Just a moment, I'll share my screen. Yep, I hope you all see my screen. So I see roughly around 50 people on the call, and it's 2x when I joined initially on February 3rd. And thank you everyone for joining on a Saturday morning, and great work by the organizers in getting this entire lined up with all the speakers. So just moving ahead with what we are trying to discuss, or what I want to show you today. So whatever we have seen by the earlier speaker, Adam has mentioned. So we'll just deep dive into how exactly it can be done, be it with audio or video or images, and where do we actually start in order to reach that point is something which at a very basic level we are trying to cover today. So we would mostly discuss about the text type of data. Also, I'll explain or refer you to the unstructured type of data as well. So hope you have been part of the earlier sessions as well. If not, there were sessions around how to getting into the ML and what is the ML engineering certification path, and also an info session. And I guess 4 or
Vasudev, I think it's muted right now.
okay,
Yeah.
is it good?
Now it's good. Yeah, thank you.
Yeah, sorry, thanks. So we all know that the ML model would be as good as the data which we give it to it, right? So now we have all been seeing from last decade that data is the new oil. Data is something which every company should bet on, and there would be a huge potential for the data. So one such example I'll give it to you from the last week with respect to the data is, so now Google Gemini want to train on the Reddit data. We all know what is Reddit. It's just a conversation, threaded conversation and collaboration, starting from some technical topics to the non-technical and the current affairs and whatever the questions which we have. So now, in order to get a copyrighted training of the Reddit data, so Google have actually, I guess, agreed about 60 million USD. I'm not sure about the number. It's around that. So now, so they are just trying to use the data to train the model and paying back to the Reddit. So we would see this kind of trend moving ahead. So when we actually think about LLMs and training those models. So now let's say if you have those, like I guess Reddit would be anywhere around over 50 to 100 petabyte of data, I'm assuming it. So if you got that level of data, how do you handle it? How do you train it? I mean, you can't directly use their text and build the model out of it. You need to do some feature engineering. So starting from that point, I'll unwrap the today's discussion, wherein it's mostly on the feature engineering. How do we handle the data? And what are the considerations whenever you do feature engineering? Again, feature engineering is a very vast topic in itself, but here we would focus on the ML certification and what are the pointers for that. And also I would elaborate on, let's say if you got some data, how do you start from day one to reach to build a model and then deploy it on top of it. So firstly, we would talk about data ingestion and what are the different patterns and data exploration. I'll also have some basic notebooks like Colab notebooks. I'll share post this session, but I have ran it already. I'll show and share the results as well. And then design data pipelines, build data pipelines and feature engineering. So one disclaimer though. So whatever we are discussing in this particular session is not the only way to do it. But as we are as part of the ML engineering certification road to that, so this is kind of curriculum which has been taken by the ML engineering certification guide. So that is the reason we are discussing that. Apart from that, whatever we are discussing today, there are multiple n number of ways to do that. So we are only discussing one such way, which is focused or in line with ML certification guide. So now let's say what exactly this week's course is all about. So once we define the ML problem, now we want to construct a data set out of it. So let's say we have 10 or 20 odd CSVs, we can't directly use it and train a linear regression model. So here we would only discussing about regression classification. Again, coming back to the day one where it has all started. So we would actually need to construct the data set and then transform the data. So when we say transform the data, so we need to build some features out of it which the ML model would understand. rather than just inputting the data. And then the upcoming weeks would be mostly on the training a model and make predictions and pipelines beyond that. So let's say, if I may ask you, so what is the most important aspect of the entire machine learning project? So you can answer in chat. Okay. Yep. So most of the answers are B. Again, it purely debatable, and it's a trade-off based upon the team, but it always revolves around the quality and size of the data which we are actually using it. So that is the reason where we have a large focus today on the feature engineering. If you consider any company which is dealing with open source LLMs or OpenAI or any other company, so they are investing a large amount of their engineering efforts in vector databases. So we'll also see what are vectors and what is a vector database at a very high level. But so whenever we deal with an unstructured data, we create a vector set of it, and we want a vector database in order to handle it. Like that, a large amount of data when we train on particular LLMs. So I understand the infrastructure, GPUs, models is important, but before that, vector databases is something which is also important in today's world. But however, if we want to, let's say if you are in an organization and let's say in the retail or supply chain space, you want to predict the demand of a particular product. So that is primarily depend upon the historical patterns. So let's say for the Christmas in December for a particular product, obviously the sales are high for a cake, let's say. Now you want to predict how many cakes I should make for the next particular Christmas, right? You basically want to understand that based upon the historical patterns and then decide it. Then you will be taking 10 years of historical data. So once you have the historical data, you would actually select the columns of your interest. So for example, it has date, number of cake, size of cake, address, postcode, latitude, longitude, and let's say flavor of the cake, and how many orders have come in a single day. Are there any external factors as well? Is it a weekend or what day we got it? So these are some of the factors you consider. So now there are two types of features. So one is derived feature, derived feature and implicit feature. So when we say derived feature, it actually forms based upon the combination of two features. So let's say if you want to generate a feature based upon the time of the day and also the day which it has been ordered, you want to create your own feature set, then that is something called a feature engineering. And also working around what are the features you want to select for a model. So that depends upon multiple multiple considerations. So if you are new to ML space, so one such approach is understanding the correlation between the features and what is the impacting feature. And it's a big topic altogether, but in this session, we would discuss how do we construct a data set and also transform the data. So how do we collect the raw data, identify the feature and label sources, select the sampling strategy, split the data. So ideally, again, when we test or train a model, so we keep certain amount of percentage of data for testing and evaluation. So we'll also see how exactly we can do that and what is the consideration. So now we constructed the data set. I'll show you how exactly we can explore and clean the data and feature engineering. So moving ahead, so in order to handle this problem, one particular framework which Google has developed over the time and currently used by major open source LLM or all the organizations is TFX. It's TensorFlow extended. So now, if you ask me, is it the best platform out there? It depends upon the use case. Is it the only platform out there? No. We have multiple platforms. Like we have Vertex pipelines, Kubeflow. Kubeflow is the another Google backed open source framework. And we also have AWS SageMaker and Azure AI pipelines. But how exactly it all started way back in 2014, 15, 16, at that point in time, this is the base for that. So TensorFlow extended. So it handles all the phases of the entire machine learning. So right from data ingestion, data validation, transformation, estimator or Keras model. This is nothing but to build a model and train it. So whenever, if you have trained a model, at least on the Jupyter notebooks or in Python, we generally write model.fit, right? So that is something which is related to estimator or Keras model. And then we can do a TensorFlow model analysis and TensorFlow serving and logging. So these are the components of the entire platform, which is nothing but TensorFlow extended. How do we use that? They are available as a Python SDK and other languages, I guess Java SDK as well. But in Python SDK, as we import like a pandas library or numpy library, import pandas, import numpy. In the same way, we import TensorFlow underscore data underscore validation. So the same applies to the other packages as well. So in order to automate this entire phases, then we have a pipeline. So we can actually design it as a pipeline. We would see this pipeline part of the model automation, model ML ops part, I guess in the week 6 towards in April. So for now, in the sessions, we would focus on the data and feature engineering. So each component here, whichever we see, like data ingestion to logging, so it has been applied, or it has been used by using example gen, statistics gen. So these are the sub packages which we can use to perform data ingestion. So these are the sub packages which we use for TensorFlow data validation. So this is just to show you what are the available packages. It's not that we should use each and every package available under TensorFlow data validation. It's up to us. So let's say if I have examples with statistic gen. So let's say if I want to understand my data set, what is the correlation and what are the features quartile range with what are the values of it? What is the max? What is the min? Ideally, if you ask me before 10 years, how do we do that? Using pandas or numpy, np.max, np.min, np.average. So this is something which at the lowest level back in 2012 or 2013, that's type of code which we used to write. So now whatever the packages which are available in the market is just an abstraction on top of it, optimized to a parallel processing and distribution processing. So now if now the data is huge, if I want to do the same np.max on 100 GB or 200 GB of the file, the in-memory, if I use a laptop or if I use any other cloud virtual machine, it fails. So that's where, when we have seen the age of Spark and it's still continuing, like PySpark, ScalaSpark, Spark SQL, that's where it all started in 2015 or 16. Before that, we used to hear Hadoop, MapReduce for these kind of processes. Right? So we have evolved phase by phase, and now we are in a phase wherein with one single function call, it would describe the entire data set, distributing across multiple core, if it is available, like multi-core CPUs, multiple GPUs, and then it get the response back. So now from the np.min, we have evolved to a larger abstraction level. Let's say if I want to do the same, whatever statistics gen done for on a distributed scale, back then I used to write np.min and then would configure a OS level code to distribute it to multiple systems and then combine it. That's something called reduce operation, and then get the response. So now all these steps is packaged and kept available as a statistics gen, right? So there are multiple packages like that in the market, but TensorFlow Extended provides one such package called statistics gen. So as the same way, we use TensorFlow transform for all the transformations, and then estimator or Keras model. So this is nothing but whenever we want to train the model or build a neural network, we use the TensorFlow or Keras model estimator. So how exactly it has evolved over the time. So when I have first used TensorFlow back in 2013 and 14, so it's at a very lowest level of abstraction, to be honest. So when I say lowest level of abstraction, now if you see any LLM or any neural network, it might be having layers. So I'm absolutely, it should have layers. The number of layers purely depends upon how complex the model is. Now, I mean, in 2013 or 14, I need to build each layer by itself, like TensorFlow layer, then decoding layer, then encoding layer, then one more layer to it. In such way, I need to build my entire neural network model, validate it, and then train it. So fast forward to now, today, I can just use implicit models. So let's say if I want a dense layer. So now the dense layer comes with its own ingestion and the layer itself, and also a activation function and validation. So this entire 4 steps, if I had to do before, I need to write multiple steps and then create each step out of it. But at this point today, I guess it would also evolve to a drag and drop stage, or with all the LLMs, we can just mention or write, like, I need a neural network model with so and so layers, it would generate the code. Obviously, I guess it's happening already with the Copilot, but we are not yet in that phase. But at this point, it's very easy to build a model, right? I mean, what's the right model fit for use case? It's again a point of discussion, but in order to develop a model or implement a model, that's easy. But again, the entire expertise comes which model to choose and what is the right features. So that's where we actually think of at this point. And then we have model analysis, evaluation, and then validation outcomes. So when I say validation, we want to check what are the how are the model performances and how exactly the model is against the accuracy, recall, precision score, and then we can serve the models. This is purely for deployment. So moving ahead, what are the exact data ingestion challenges? So we have already said that the ML model would be as good as the data which we give. So one such example recently is on the LLMs, where it gives sometimes the random response, and that may be due to the amount of data it has been trained and the patterns has not rightly recognized. And there are huge models, like trained on billions of parameters, but whatever we are starting from is, let's say, 1 GB of data, and if we can't determine the right features and doesn't train the model in the right way, I mean, that can be evident using the model overfitting or underfitting. That means the model has learned the patterns in a very high fashion that whatever comes in the data, but obviously it packets into one of the potential label and then gives it as an output. And efficiently utilize hardware and decoupling loading. So now decoupling loading is one of the important aspect. As a beginner, if let's say if I want to train a model, and I would do everything on my laptop. I mean, that's how I learned it back in last decade. But at this point, we have multiple tools to do that. Let's say Snowflake or BigQuery or Spark. So what exactly it does? We are saving the data separately. We are saving the, I mean, we have the compute at a different place. Whenever I want to do the feature engineering or do data transformations, at that point in time, I'm bringing in the data and trying to process it and save it back. So that's something, I mean, previously it used to be a very tight coupling between the data and compute. Now it has been changed. I mean, why exactly it is changed? I mean, the reason is when the data size is increasing, we would obviously look for distributed computing. So now when we say distributed computing, keeping a copy of data in across all the compute instances which we have is a costly job, and it's not a good practice as well. So if you read about how Spark works or how BigQuery works, it has something called shuffle operation that would actually distributes the data across all the distributed compute instances. So now let's go to the core DF TensorFlow engine. So df.data is one of the function from example gen. So what exactly it does? So df.data reads the data from memory or storage. So this storage can be external or internal. When I say internal, it can be from your own environment, or when I say external, it can be from a blob storage like Amazon S3 or Azure Blob or Google Cloud Storage. So it can parse multiple file formats like Parquet, which is generally used in ML. I mean, that again depends upon the use case, but I have generally used the Parquet format. And then it transforms the data like text vectorization, image transformations, video sampling, shuffling, batching. So if you see what exactly is a video temporal sampling, we'll just speak about audio temporal sampling for now, because in the previous lightning talk, we have seen how exactly it performs, right? So now if I have submitted my own audio, it would sample the entire audio. Let's say if I'm doing the same thing with tf.data, for example. Right now, I create the data and submit it to GPU. What my tf.data transformation does is it would remove the sounds, for example, sounds firstly, and then it would retrieve the sounds of our interest, and then it would sample based upon the timestamp, and then it would give it to the model for inference or training. So I'm just saying an example of audio because we have seen it 20 minutes back. Now let's say, what is text vectorization? I have a sample of how text vectorization looks like. I'll show that. So now how exactly it is different and what TF data would give us above what other platforms can't give. So you may ask that why exactly I need to use TF data? I can use pandas or I can use any other similar package, right? So one consideration is whenever we are trying to use tf.data, so TFX is inbuilt connected with GPUs, TPUs, and I mean CPUs obviously. So earlier, if TFX is not in place, how do I used to do that? Is there is something called C++ CUDA libraries. So I need to first install my OS, and on top of that Python, and top of that CUDA libraries, and on top of that I need to run my code to connect to the CUDA libraries. I mean connect to the GPUs via CUDA libraries, and then try to train my model on top of the connected GPUs. So this is a large problem. So now this entire problem is abstracted or eliminated by using a platform like TFX. So when we say accelerators is nothing but a GPU. So the processing capacity of GPU is something which is evident when compared to the CPU or the time. So that is the reason, coming to the today's world of LLMs, every every LLM model is trained on a GPU. So be it any GPU, but it's trained on a GPU. And also Google has went a step ahead and trained on their own tensor processing unit TPUs, which is way faster than the GPUs which others use. So now we would come back to again to discuss about the data ingestion example. So how exactly I can ingest my data? So let's say we have preprocess function. This is nothing but a data transformation. So let's say if I have read my TF record, after reading, I mean, this can be CSV or Parquet or any format. Let's say I have read my CSV file. And on that point in time, I want to eliminate all the null values and eliminate all the white spaces and eliminate like let's say serial number column from the first and updated time and updated inserted time from the last. So all that business logic would be going into the pre-process. So once we read the data on that data set, I would first do a map. Map is nothing but for every record, apply the business logic which has been there in the pre-process function. So this reads the data from TF record and then applies the user-defined pre-processing. That's nothing but the business logic. And then it actually batches the data for training efficiency. I mean, I'll explain this, what actually the usefulness of this when in the upcoming slide. And then we can use model.fit. So this is the transform phase of the TFX platform. And then this is the model estimator or keras, which we have seen on the other slide. So now how exactly it's using the resources. So in this sample, or in an ideal world, if we are using CPU and to train GPU, what used to happen is CPU would unload the data to GPU once it prepares the data. So that is the reason we are seeing ideal time here. So now let's say if we try to do this in parallel, right? So now the CPU would prepare data and give it to the model. So how exactly it can be done, right? So for that, we used to use something called prefetch. This is nothing but X can be any number of the buffer size. So let's say if I have put like a buffer size of, let's say, 10 or 30. Again, this purely depends upon the data which we are handling. If the data is 100,000 rows or 200,000 rows, again, it purely depends upon how batches of the buffer size we put it. So now prefetch is nothing but, let's say, now the map process has completed the processing of first 10K records, right? Now what prefetch, or the meaning of prefetch is, once it's done, push it to the model.fit to train. So that is something which we can enable the parallel data transformations. And then moving a step ahead, can we do the data transformations in parallel, like parallel maps? So I mean, ideally what we have achieved this is a sequential map. Can we do it is in a parallel? Again, that depends upon, I mean, the amount of CPU which we use, but the suggested way is, if we have the multi-core CPUs in place, we can actually do that using this particular prefetch batch, and then adding this line, number of parallel calls. So auto-tune is nothing but, it purely depends upon the available CPU cores, and also it depends upon the number of parallel threads the current in-memory can handle. Of course, if you are today starting up learning about ML models and train the models, this would be relevant. Let's say if you are trying to use already trained models to build anything on top of it, this would not be relevant. But for the ML certification, this is something which is important. So now for the parallel extraction. So how do we extract the data in parallel, like at a single point in time? How do I do IO operations? So this is purely depend upon the OS level. I mean, in Python, we can make it multi-thread using multiple external packages, but this depends upon the CPU capacity and the OS level. So how exactly we can do that? By using the number of parallel reads. So this is one more parameter which we can use to actually read the entire data set in parallel. So I mean, the significant difference of this and parallel reads is truly when we would actually handle a large scale data. Let's say we are handling 200 GB of data or 1 terabyte of data, then it matters to be truly parallel and in a distributed way. But when we are just handling 1 GB of data, you might not see a significant difference altogether, right? So now we have seen how to ingest the data. It would ideally be any type of data. In the example, we have seen TF record data set, I mean type of data, but it can be CSV, Parquet, or any columnar storage, or connecting to any external system and getting the data, right? So moving ahead, now we would discuss about TensorFlow data validation module. So what exactly is TensorFlow data validation module? Let's say once we got the data into our disposal, now I want to analyze how the data set looks, how exactly the data can be when I say manipulated, it's nothing but generate the features or change the data, right? So that is the end goal of using TensorFlow data validation module. So I would explain this with a simple notebook. So I've already executed this in the interest of time. So I'm actually reading a sample data, which is available in the open source. It's from Kaggle. So here I'm using a TensorFlow data validation module, and I want to visualize statistics of my entire train data, right? So how exactly, I mean, I'll just show you how the data looks first. So this is the sample data, latitude, longitude, and housing median range, total rooms, bedrooms, population. This is some kind of housing data. So now I want to run the statistics. So this is an inbuilt function. So let's say if I don't use TF data or anything similar, what I end up with, I need to read the entire data and do a pd.min, pdmax, like dfmin, dfmax for each column, and I need to understand what is the range of data and how many zeros are there, right? Standard deviation mean. So this is important in order to understand how the features are correlated to each other. I mean, we can build the correlation on top of it, not from this what we see, but let's say if I want to understand the quantile range. So what is the data distribution? From this, what I can understand whether the data is skewed or not skewed, and let's say if it is skewed, how can I exclude some outliers or bring in some range? So the generic approaches are by using log or standard deviation or running some tests on that, right? So when I use log, it comes like from the large variation of the data, we actually reduce the dimension of data, right? So there are certain like highlighted ones, like if the data is missing by some threshold, it would be actually shown in red. So this is one such example. Now this is for the numerical features, I guess. And yeah, this is for numerical features. And this is for the categorical features, right? So payment type, right? So which is in cash and credit card. And there are some more occurrences, but we don't have data for that. And what is the maximum, like maximum times the payment type, right? And then we can infer the schema as well. So I'm again using tf.data validation and infer schema. So I can understand what is the schema looks like, features look like, and domain, company. This actually matters when we have nested fields like JSON, right? In that time, we actually understand the domain. So this is to understand the evaluation score. We have training data and testing data. We want to apply the statistics on the train and test and understand the statistics. I mean, this can be explored offline. I'll just share the link of the GitHub for this. And in the interest of time, we'll just move ahead. So now, what exactly the data validation can do? So it would generate the, feature column. So it can be numeric, categorical, or bucketized. So this is nothing but using one hot encoding. We can actually encode each and every label. So again, coming to the 101 basics of ML, a machine learning model cannot understand what is red, what is green, what is blue. Of course, if it understands it as a text. And let's say if I apply linear regression directly on red, green, blue categorical variable, it just understands the particular row is red and how many rows are red and when it is occurring with the other columns, but it can't really understand the pattern. So that is the reason we go with encoding methodologies. So one such methodology is one hot. There are multiple encoding mechanisms like zero shot, one hot, like building the embeddings, right? So we have three basic ones. For categorical, we generally do one hot encoding. For numeric, let's say for image generation, I just wanted to recognize what is the number which I'm predicting. So for that, like 0 to 9, for that I use element vector and bucketized cross embedding. Just a moment. Yep, cross embedding. So numeric categorical generally go with one hot encoding, and feature crosses purely depends upon the use case. So let's say if we are dealing with latitude and longitude, a location. So now in order to determine a geographical location, I need both latitude and longitude. In such case, I can combine them, and that ideally becomes a feature cross. And we would see about embeddings in detail in the demo. And other examples are like hashing. So what exactly hashing looks like is, a hashing is nothing but when we have n number of categories across multiple ranges. So let's say if our data changes in the future, the number of the number of categories of that particular feature can increase, and we don't have any limit on that. That can be a potential hashing function. So now, how exactly we change the range of this particular feature dimension? So now let's say my first value is of 1 and the last value is 10,000. Now I have only 100 data points across this. So this particular pattern may be very sparse. The reason being, I have only 100 variables across the range of 10,000, and all my data lies in, let's say, 1,000 to 5,000. Now, in such case, I mean, the entire data set feature is sparse. That's the meaning is I have only few data sets at certain range of interest. I want to change it between the range. Right. In such case, these are the top techniques, but we have other techniques as well. So I generally use not only myself, but generally the practitioners use log scaling to get down the data range whenever the data is skewed. So let's say how exactly the logarithm application looks like. So when we have a ticket price, for example. So if let's say if I want to travel to US, I see the price as, let's say, $9,000. Now, if I want to predict 9,000 and or as 10,000 or 8,000, that should be okay. But let's say if I estimate the 9,000 as $500, that is way differentiated, because this depends upon the data which we have. We only have 9,000 couple of times, and at all the um, seasons other than peak, we have the data around 1,000 or 500, for example. In such case, the patterns of the data are skewed. So in order to bring in the entire data into one single range, we use log scaling. And for handling outliers, we generally use, if we keep the upper limit and lower limit. If that crosses that range, keep it as a max is something which we say. This purely depends upon the pattern. And again, this is the reason we use data validation in this case, to understand the max and min values and what are the outliers, what are the percentage of missing values, and if there are missing values, how do we replace them, or should we ignore them if that doesn't signify? How do we understand which which row signifies and which doesn't? That depends upon the correlation, and for that we do some more analysis on top of the data. So moving ahead, so if you can see here, this zoomed out, but let's say my raw feature column is ranging from 5,000 to 45,000. But when we use this kind of normalization techniques, right, my entire data can be coming from 0 to 1 or 8.5 to 11 when I use logging, and z-score is mainly between negative and positive. And clipping is nothing but we are just restricting the outliers of data. Let's say if I put a hard limit of 40,000, whatever the data which is more than that would be assumed as 40,000. So that is something called clipping. So now, how exactly the possibilities of feature engineering can be there? So before that, I'll just show you what and how an embedding looks like. So this is what a embedding in the latent space looks like. So I'll just show you, it should be, I'll just refresh it. So this is what a embedding looks like. So this is the famous 𝗦𝗃 feature embedding, which is first released by Google back then. So let's say if I want to understand about software. So what are the nearest points to it? So today, if we are seeing LLM can generate the like answers, and what are the nearest words to that? So it has all started from this 𝗦𝗃 back in, I guess, 2015. But however, we can see the nearest neighbors to it based upon the cosine similarity and Euclidean distance. So let's say if I search with a word called software, it would give me all the words related to that original space. I mean, we understand that these are the nearest words to that. How do we actually get to this point that this word is near? This again depends upon the feature embeddings and the corpus of data which we train on. So the entire text analytics on NLP space have actually started with the word2vec as a entire like exponential curve. But before that, we used to do a basic NLP or text analytics. But this is kind of a basis for what we have today, like LLMs and other text analytics tools. And I've trained it on my own data set just to show you. So we can also train it on our own data set. So let's say if I have my own data in order to train. So this is how the entire vector space looks like. So this is a three-dimensional. This is generally known as eigenvalues for each value. So let's say if I want to select a single variable, I have selected my label of interest as what. So all the nearest words to that in the latent space are displayed here. From this, I understand what my corpus is. And I mean, this is a pure English, but this can be of any language, or this can be of images as well. For example, if I show for images, this would take some time, but if you want to build your own image data set and train any model or features on top of it. So let's say this is the famous MNIST data set for image recognition. This was again back in 2016 or 17. So now if I'm selecting it as 4, it would show me all the images which are similar looking like to 4. Like these are the neighbors, 4, 4, 4. Sometimes machine learning model is always evident to fail in certain cases. Like that is somewhere where it recognizes 4 as 9. So this is the input data which we prepare and make the machine learning model understand that this is a digit 4 and all the nearest. So how do ML model understands what are the nearest neighbors to that? What exactly others images which are alike 4? So that depends purely upon the distance of that particular point in the latent space, which is the eigenspace. I mean, generally it calls as latent space, but it purely a eigenvector with a three-dimensional vector. So just to move ahead in the interest of time. So where exactly we can use a feature engineering? So it can be done in multiple places. Before ingesting the data, once the feature is created, or training the model. So we'll see pros and cons for that. So let's say if we do a training, I mean, features training at the training model level. So we have TensorFlow, efficient TF models, and input method only. But let's say if we do at a feature creation and all the features at this point. So ideally, the feature engineering should be away from the core model training is what I believe in. The reason being, so if you're working in an organization setup, you might be having a large number of teams working in the same set of features. So that's where a concept like feature store came in. But if we are, in order to simplify the entire discussion here, I'm just focusing on, let's say, 10 features. If I do a 10 features at the train model level, so that is a costly operation because already I'll be crossing all the feature creation. If something fails in the train model level, that is a bit difficult to handle. And then we have efficient TF methods and aggregates at the feature creation. And then we have pre-processing. So in pre-processing, we just eliminate the data and select the right data. So this is away from the ML. This is mostly a data engineering space. So once we do that, imagine a model to predict the length of rentals. So we have a station name and start date as input and day of way. So this transform, let's say we are keeping it as a separate and not in model. So now the ML model would be actually giving us the duration. So this is nothing but giving the input of, I mean, this is mostly around the bike rental. So let's say if I give it as an input, it should give me how much time a particular customer would renting a bike is what the data set is all about. And when I give a business transformation here, it actually computes and gives the duration as an output. So this is the more or less the entire transformation pipeline. So inputs, pre-processing, feature creation, training the model. So ideally this pre-processing and feature creation is kind of a transformation. So I'll just explain you what exactly is this. So what happens is once I train the model, so the model is oftentimes trained on a transform data. So when I transform the data, I apply some business logic. If I don't apply that business logic, whenever I'm doing an inference on top of my incoming features, ideally the amount of data which I train or the data skewness would be evident. So just to simplify, I have trained the model on a data skewness of 1 to 100 and applied on a log transformation on it and supplied that as a feature to my ML model. In such case, my model is trained on a log value of that feature, right? So whenever I do a prediction or an inference on the trained model, what happens is the incoming data would be 100 without log transform data. So now in order to, like, let's say if I directly give a data point of 100 to my particular ML model, the ML model would show a incorrect result. The reason being the model trained on a log of 100, but I'm just giving the 100 value as a input. So now this increases the data validation skewness. I mean the prediction score also comes down. So for that reason, when we do it with the transform function, so this actually consists of the entire transformations of features as well. So what it means is whenever we train some model or build some model on TensorFlow, it actually creates a model graph. Model graph is nothing but get the data. Let's say if it is a neural network, layer 1, layer 2, max pooling layer, min pooling layer, evaluation, activation function. These are the model steps, let's assume. So all the model graph is saved when we train, and when we also do a prediction, right, we can directly use that feature engineering transformation from the model graph. So again, it entirely bundles the abstraction and we can just use a transform function. So that is the main aim of using the transform in order to directly apply it whenever we are using a ML predict. So this is how ML graphs look like. And whenever we actually see like drop off, scale, dense features, this can be again reused across multiple models, and also it's easy to push to the prediction based upon the values of all the metrics which the model output is of. So now if we bundle up with the entire model graph, so as I rightly said, the model graph would include all the transformations, and whatever the input data during the training, inference, and evaluation is, I can give the data as is. This transform module, which consists of my business logic, would already compute all the feature engineering, derived columns or the changed features, and let's say upscaled or downscaled features to the ML model and gets the output right away. So I'm at the end of the session today. So I'll share all the links. Before that, one question on the feature engineering. So let's say we have different cities in California. So this is mostly on building the features and what is the right feature in this case. So now the end goal is which of the following sets of feature crosses could learn city-specific relationships between rooms per person and housing price. So any guesses on these answers? Okay, I see the options as A, right? But let's discuss each of it. When we have three separated bin features, so we have a latitude and longitude and rooms per person, right? So the question, it's clear that we want to understand the location and city specific relationship. If I want to understand which city it is, I need to understand the geographical location. If I want to understand the geographical location, ideally I should have latitude and longitude together, right? I don't think so. With bit poor in that, but with single latitude or longitude, I cannot get the exact location. So with latitude and longitude, I mean, the entire idea here is we need to have a longitude and latitude together, right? And now we have a rooms per person. So rooms per person would be truly dependent on how many rooms the person has booked on a particular date for that particular hotel booking, for example, if we understand. Sorry, not the hotel booking, houses price. So my bad. So now we want to have that rooms per person variable included in the geographical location with the city specific relationship. So that is the main reason. Again, we need the binned latitude and longitude. The reason being, we want to understand the specific features to be in a set of constant hard limit range. Because let's say if in California, if the outlier is beyond the central region, so then it might be an outlier. So for that reason, I mean, the correct option is D, to create one feature which understands the entire relationship, because it says city specific relationship and rooms per person. So for that reason, the right option is D. And thanks for all the ones who have answered. And now I open the floor for Q&A. And post this session, I'll share all the material which I've seen and all the links which you can go and learn more about it. So I do see some questions on the Slido.
I can share the Slido screen.
Yeah, please.
Could you please stop sharing this?
Yeah, sorry for that.
Sorry about that. We can start with the top question. When outliers in data uncover new insights or breakthrough, how can we distinguish between noise and valuable outliers?
So that's an interesting question. So for example, I mean, what I have experienced is, so we know that we didn't know that COVID was coming, the pandemic. So all the sales, so I was back then working with Ford Motors, and I was actually checking on the Ford F-150 pickup truck sales. So it got suddenly dropped in 2020. So now I didn't know that what is the reason. I mean, when I say our machine learning model didn't know that what is the reason. So I mean, COVID is an outlier. We all know that. It was never been before, right? So in such situation, the outlier is something which we need to consider. However, couple of assumptions here. Not always a single outlier would impact the model in a positive or negative way. Ideally, we should remove outliers because we are not tuning the model to see the actual data which we are putting out there. We are focusing the model towards what the noise is. So again, the second part of question, how do we distinguish between noise and valuable outliers? So the valuable outliers are purely dependent upon the multiple external factors as well. So in my case, I have assumed one more data set, which is COVID data, which was available, and that has impacted my data. So let's say if I want to take a outlier of sales of a particular chocolate. So now let's say if I'm near to a weekend, or if I'm near to a particular, let's say Christmas again, so my chocolate sales have been shoot up a lot. So here we couldn't determine it by the single data set which we are handling, but we should or dependent on the external data sets. So by assuming some external relatable data sets, you might derive or differentiate between the noise and valuable outliers.
And then we have the next question. TensorFlow extended looks like an ETL no-code solution. Is it worth learning the tool rather than the pipeline itself?
Okay, so yeah, this is an interesting first time impression which I had to. But what exactly it is, let's say we bundled a model. Now, ideally, in an ideal world, what used to happen is, if I train some model on TensorFlow, I need to go back to a different framework and get the data in a TensorFlow compatible way, and then publish it, and then get the model results. So I am talking about 2013 or 14. So now what exactly the Google has done is it has built some compatible components. So in order to answer that question, it's not a no-code solution. You should still code, just that it's a coding at a very high level abstraction. But of course, if you are a research scientist or doing a PhD thesis, then you should go back into the lowest level of abstraction and build from there. But as an engineer myself, I don't see, I mean, there is a value, but considering the business demand and fast to the market, I consider using frameworks like this.
Yeah. Then I think we have one last question for pre-processing. How do you usually handle missing data?
Yep. So this is a common question and interesting one when we actually use TFX. So out of the box, TFX provides few functions to replace missing data with average or with min or max. That is the general way of handling it. However, we can build with TFX, we can build some custom functions. By theory, if we go, how do we handle missing data? So we first need to understand the pattern of how the data is varying, whether it is skewed or whether it is not skewed. Let's say if it's skewed, you need to first bring in the data into a certain distribution. I mean, in an ideal world, I would say normal distribution, but that is not possible when we handle the production data. So we would then see whether, what percent of data is missing. Let's say if the data is missing only 2 out of 1,000. So we would do a risk analysis. What happens if I miss those 2 rows? So let's say if those are evidently impacting the entire pattern matching, then I would see whether how exactly I can do that. What is the nearest value to that? Let's say if I'm handling the time series data, I would replace it with the +1 or -1 data. Let's say if I'm handling a kind of classification or categorical data, I would do a reverse engineer and understand whether it is possible to replace it with any nearest category. How can I do that? Again, I can do with the correlation of the categories available in that particular ML, machine learning, problem space. Sorry.
Yeah. I think that is the end of our questions. Thank you so much, Vasudev, for giving us your precious time and giving the very informative session. I think we are all thankful for your expertise and for actually answering these questions in the right amount of detail. Thank you so much for coming. Next.
Yeah. Next, we have an announcement for the upcoming sessions. First of all, yes, Vasudev and Adam, thank you so much for working with us on this one and investing your time, with us here. We really appreciate it and would like to see you in our upcoming sessions too. For the next session, as on the screen we can see, it would be on March 9th. The topic is machine learning in enterprise, and we'll be focusing on more hands-on, more diving deep on Google Cloud tools and how to train the machine learning pipeline, etc. So please stay tuned. Look at the session plan, everybody. We do encourage you to prepare yourselves, before attending these sessions to help yourselves get better, hold of it, what we are discussing, because these sessions are kind of the review of the overall content from Road to Google Developer Certification focus on machine learning. So if you could prepare, those courses that we have listed, like on the screen, if you see, there is a course listed as machine learning in the enterprise. So if you come prepared, you would have better questions for our instructors, and that would help you prepare better for the certification, or in general would give you a better idea about the topic. So we highly encourage you, and if you have any issue going through the labs, or if you don't understand any key concept, please ask for help in our Discord channel. I think we exceeded time. Thank you everybody for joining. Yeah, we'll see you all next time again. Thank you, Adam.